Hello guys and welcome back to the series. Today we will jump into Fusion 360 and start designing the beam of the gantry, which is going to be a lot of fun. But first off, we will be taking a quick look at the criteria for judging which design will be the best. Alright, taking a look at the criteria, I've decided that the best beam will excel in the following criteria, and that would be weight and simplicity, like how simple is it to build, and not only manufacture, but like build in your garage without needing too many tools and expensive equipment. And then we will judge how great the design is by the availability of materials. It could be that we end up designing a really good beam, but it needs special and thick carbon tubes or something that is hard to come by. And then the last property that we'd like to have for a criteria is vibration dampening, and that basically means how well the beam can absorb vibrations. That is also hugely important because the router will have a motor with an end mill spinning at probably like 18,000 RPM, so we want to suck up as much as that vibration while cutting as possible. Alright, the beams we're going to design today is the four most interesting beams, I think. Perhaps there's one more that's pretty interesting. I've already designed all the beams, but I just felt like showing you how I did it and how I went about it, so that you can simulate your own beams as well. You can see that all the beams, right now we're looking at the cross sections of the beams. All the beams have rectangles, and these rectangles represent linear rails, and they are 20 by 20 millimeters. And all the materials are aluminum, and this right here is epoxy granite. Yeah, and talking about materials, I'd like the beams that requires some sort of processing, like drilling holes to install the linear rails. I'd like them to be aluminum because it's cheap and it's easy to work with, especially for us hobbyists at home. Yeah, all right, let's get to it. Let's jump into Fusion 360. Okay, I've gone ahead and saved the file, and we are ready to start sketching. So I'm just gonna go ahead and draw the cross section for the first beam. And one important thing to note, a little tip, is to create your beams so that they are centered in the origin, so that you can mirror rails and other features around on the part. Without creating extra work planes. So I'm gonna go ahead and find the center rectangle tool, and I'm going to draw the cross section. And I know the dimensions, it's 120 by 20 millimeters. No, wait, by 25 millimeters. All right. So another thing I forgot to say is that the dimensions for all the beams will heavily depend on the availability of the material. So that is also going to be a limiting factor in our design, because we wouldn't want to end up with something that we cannot buy. All right. All the beams are going to have a length of 600 millimeters, and remember that thing about making the part at the origin. Well, we can actually create a symmetric extrusion, and first off, it's going to be half of the length. That means it's 600 millimeters from here to here, which we don't want. We want the entire beam to be 600 millimeters, so I'm gonna go ahead and press whole length. All right. Next up is modeling the linear rails. I know they are a bit simplified as rectangles, but for these kind of simulations, we are not looking for the exact result. We're just looking for something that's rather close to what the real world stiffness and deflection would be. So I'm going to go ahead and extrude that, and instead of making this 600 millimeters, then if I later on decide to change the length of the beam to 700 millimeters, I'd have to go back and change this as well. And if I get that, we could have some kind of error. So there's multiple things I could do. I could go back to our first extrusion. I could hover over this this little text box for the distance, and as we can see, it gives us a name, a variable name, that's D3. That actually means that if we enter D3, our value of 600 millimeters is stored in there. So I could go ahead and extrude this one again, and I could enter minus D3 to get it in the correct distance. Another thing I could do is to extrude it up to a face. That's usually what I do. So I'll just have to select the face right there, and it extrudes all the way 600 millimeters. And this will update as well if we decide to change the whole length of the beam. Alright, as you can see, it connects to the body, and that means that we cannot apply a separate material to our rail. So I'm gonna go ahead and make it a separate body. And I do that by pressing a new body under operation. Alright, we need two rails, of course, so I'm gonna go ahead and mirror the first rail. So I'll find the mirror tool, and usually the mirror tool goes to faces by default, so we can only select faces. We don't want that. We actually want to mirror the entire body, so we can go ahead and select bodies, and now we can select the whole body at once. One thing I prefer to do, which is also a bit more efficient, is actually selecting whatever we want to mirror first. That could either be the body or the extrusion down here in our timeline. Now I'm just going to go ahead and select the body, and now if you press the mirror tool, you can see that it has selected bodies instead of faces, so it automatically goes to whatever we have selected, and that saves us those two little clicks. Alright, I'm just going to go ahead and mirror that around the origin mirror plane, right there, and press OK. Now the first beam is almost ready. We just need to apply our materials, and I've linked my materials up here, but if you don't, you can find it under the modify section. If you press this little setting icon, you can pin it to your toolbar, and it should appear up here. Okay, for the materials, we are going to apply stainless steel for the rails, for the linear rails. No, they're usually made of hardened steel, but the Young's modulus, basically the stiffness is so close that it's not going to matter that much anyways, so steel would be fine. And then aluminum, I'm not going to select the default aluminum because I know what type we will be using. We will be using one of the most common types, and that's 61 aluminum. And that's hugely popular because you can machine it. Okay, now we are ready to insert the simulation workspace. And I will double click on static stress. That is the type of simulation that we will be doing in this video. And right here we have our simulation workspace. Okay. Today we will mostly be looking at the materials section, the constraints and loads, and then the solve button, and of course the results, which gets us to a different set of tools in the toolbar. Okay, if you're unsure that you have selected the correct materials, what you can do is that you can go to the materials section, and you can actually also edit the materials right here. You should be able to do that. Oh, and we can see the properties. Didn't know that. That's really handy. Yeah, so you could see that the Young's modulus for stainless is 193. For hardened steel, it's usually about 200, or perhaps a bit more sometimes. Okay, I'm going to give this give this beam some constraints so that it behaves the way it would on a machine. And on a CNC router, these faces would be bolted to some sort of leg for the gantry. So we're going to fix those. And I'll just press the constraint, and then we can just select the faces. And as you can see, this little log appears, and that means that it's fixed, as the type is selected right here. You have different types, but we're not going to talk about that today. I'm going to press OK, and now we are ready to enter some loads on this beam. Okay, if we look at this beam from the bottom, and if we put up some sort of Z-axis here, you can see that the load while cutting would come from down here. So we want to simulate that, because that induces some different kinds of stresses compared to just making the loads come straight on the rails like this. So I'll select my two faces. That will be the linear rails that the force is going to be applied to in the real world. And then I'll select remote force, and I'll drop it down 150 millimeters. And the force we will induce on this beam will be 1400 newtons, and that is almost 140 kilos. So that's quite a lot. Okay, now we have all our parameters and constraints entered, and we are ready to simulate. I'm just going to go ahead and press the solve button, and this little menu appears, and you could either solve it locally or on the cloud. Now if you do it on the cloud, it's going to take a few seconds. It's going to take up a few seconds on sending this model to some kind of server, and then receiving the results. And now, because this model is so simple, for me it's actually going to be quicker just to solve this locally, and that might also be because I have a decent computer. Okay, when you have solved your beam, you will enter the results section automatically, and you can see our constraints and material section has disappeared, and we are presented with some new tools. And the first thing that could be pretty handy is the deformation, and that basically adjusts how much our beam would move under the applied load. So this one is underformed, and we have actual. That's how much it actually moves. That's hard to see because it moves so little. And then we can see adjusted, which basically overdoes how much the beam deflects. Okay. Right now we're looking at the safety factor. We don't want to look at the safety factor. We're actually mostly interested in the displacement, and that means how much the beam has moved. And the first thing that I note is that it's not uniform. I'm not sure what's going on there, but I'm not interested in the result we have right here, this probe. I'm going to go ahead and create a new probe under the expect section, and then I'll press I'll apply that somewhere in the middle of the beam, and there we have our number. So we can see that under a load of 1400 newtons at a distance down of 150 millimeters from the center of the beam, then we get a deflection of 0.01 millimeters. Okay, now this is where it becomes really interesting to have FEA available to you, and FEA stands for Finite Element Analysis, and that basically means computer simulations, as we're doing. I was going to say that it's really interesting because if you're wondering how much stronger this beam would be if we made it 5 millimeters thicker, then you could easily do that by going back to the design to the design suite and then just change the thickness. Let's say, or perhaps we could make it 20 millimeters if you wanted a machine a little less capable but a little lighter and cheaper to build. Then we could go back into the simulation workspace and we could resolve the whole setup. And all we have to do is just to press the solve button again, because we have already fixed the two ends and our load is still here and it's the same and it's still applied to the rails. So I'm just going to go ahead and solve this again. And there we go. Now we can see that we have a little more displacement. I believe it was, and I believe this one has 0.003 millimeters more deflection, somewhere around there. So that's pretty interesting to see actually how much more deflection we get when we make the beam 5 millimeters thinner. Now I don't want to use this result, so I'm just going to go back in and redo what we had before. It was 25. Okay, and I'm just going to simulate that again. And there we go. Now we are back with our original results. Okay, let's go ahead and create the next beam. So looking at the first beam, I can see that we have a lot of displacement down in the lower area of the beam. So I think it would be really interesting to see what happens if we make an L shape, and then hope that some extra material right here in the back would create less deflection. So let's go ahead and do that. Now, in order to make this fair, we are going to make it so that the cross section has somewhat of the same area of the cross section from the first beam. So I'll go back here in the design, and I want to make this area the same as the area in the L shape. And if we look down here, if I click on anything, a length or a face, I can see a measurement down here in the lower right corner, and it tells us that this has an area of 3,000 square millimeters. So we're going to aim for that. I'll create the L from two rectangles, and I'll make both 20 millimeters. And it should be 120 millimeters high, and we will make the bottom 40 millimeters. Where does that leave us? Let's see. This beam will of course be 600 millimeters as well, same as before. Now let's see the area for this cross section is 3,200. So perhaps we could make the leg of the L, if you will, a bit shorter. Let's try 36. A little better. Perhaps 32 millimeters. Yeah, that's almost spot on. That's almost 3,000 square millimeters. Now I think this looks a little funky. I intuitively think that the bottom of the L should be a little longer. So what I'm going to do is that I'm going to make this a little thinner instead, and then make it longer. I'm going to delete our constraint here that makes this side equal to that side, and I'm going to make it 15 millimeters, and then we can make this one a little longer again. Yeah, there we go, exactly 3,000 millimeters. That's great. Okay, I'm just going to go ahead and save this design as well. You cannot simulate anything unless you have saved it. Now we need to create our linear rails. I'll press R for rectangle, and I'll make this 20 millimeters. Now instead of making both sides 20 millimeters using the dimension tool, one thing that would be a little cleaner is to make the sides equal by using the constraints up here available. That just saves us a dimension, and then if we want to change this, it updates both sides, which is handy. Okay, now one thing I forgot to do is to make it symmetrical. So our beam is not symmetrical. It's not centered on the origin. So if I want to mirror this this part, I'd have to create a new work plane. I'm going to show you that. So what I'm going to do is that I'm just going to go back into our sketch and make everything symmetrical. And I'll just click on the origin here, and I'll delete all these constraints. I'll select this, and I'll just reconnect what needs to be reconnected. There we go. Oh. There we go. And I'll press, I'll use the midpoint constraint, and basically says the middle of this line to this point. So we're going to use that, and I'm going to go ahead and press OK. Alright, now we can mirror our rail, and I'm going to select the rail before using the mirror tool, if you remember. And then I'm just going to select the origin, the correct origin plane. Now we're ready to apply our materials. So I've actually saved our materials under my favorites library. So I'm just going to go ahead and drag and drop the required materials and then enter the simulation workspace. Okay, the setup is going to be the same as before. So I'll just fix the ends. One thing that is important to remember is that we don't want to fix the linear rails, because they're not going to be fixed to the legs of the gantry. It's hardened steel, so we're not going to like drill and tap some kind of hole for a screw to go in. So I'll only select the ends of the main body of the beam. Okay. And if you wanted to verify that we have the correct materials, you could do that the materials section. I'll go ahead and apply our loads, and I'll select the rails, and I'll make it a remote force, same as before. Remote force of 1400 newtons at 150 millimeters below the center of the beam. And now we are ready to solve. Okay, now the next beam is going to be really interesting. The next beam will be a hollow profile. And it will have the same dimensions by 40, and I'll make this 10. Okay, this looks a bit weird. I'm going to make it a little wider. That looks more like it. Okay, and yeah, the next beam is going to be really this beam is going to be really interesting, because it will be filled with epoxy granite. And what is epoxy granite, you might ask? Well, epoxy granite it's kind of like cement, but with a few different extras in it. It's a mix of materials blended together, and then they're held together with like 20% or 15% epoxy. And what this does is that it's really great at absorbing vibrations, which is very desirable for our gantry. So it's a quite good material for the application. Another thing is that the epoxy granite also adds a bit of stiffness. So I decided it would be a good idea to simulate a hollow profile, and then fill it with epoxy granite and see what kind of results we get. So I'm just going to go ahead and create the rails, the linear rails as well. I'll make those really quickly, 20 by 20. Okay, and I'll just press Q from the sketch environment, and it throws us straight into the extrude tool. There we go, and I'll make it a new body. And now we can mirror it. I'll press the mirror tool. Alright, there we go. Now we want to model the epoxy, and one thing many of you guys might do is just create a sketch and project the geometry to get this section right here. Another thing I would suggest that you do is just reuse our first sketch by going under the sketches and then press the visibility icon to make it reappear, and then from here we can actually select it, and then we can just extrude it up to the end, and we'll make it a new body. And we actually wanted to extrude up to both ends, so I'm going to go ahead and select symmetric. Another thing that you could do instead is go in and extrude, and you could make it. Let me just select the first face right here. And you could select 2 sides, so extruding to 2 sides instead of symmetric. And then it asks you how long should the next side be extruded, and we want to make that up to a face as well, and that face would be the other end. So they're both eligible solutions. The last one with 2 sides is usually more for a different scenario. But it works as well right here. But usually I just go with the symmetrical, that's a bit faster. And then we can just go ahead and apply our materials. Okay, now you're probably wondering whether or not you can apply epoxy granite, and I'm going to go ahead and tell you that it's not a part of the standard material library. Like you can see right here, you will not be able to find it. They do have granite, but not epoxy granite. So what I've gone ahead and done is that I've created my own material. And if you want to do that really quickly, just copy my epoxy granite. You can do that by going to modify and then manage materials. And what you'll have to do is that you'll have to copy any material from the Fusion library and then add it to your favorites, and then when it appears in the favorites section, then you can edit it. You cannot edit it if it's a part of the Fusion library. It will not allow you. They're all locked. Now when your material appears, you can rename it or whatever, and then you can double click it to enter its properties, and you can adjust the appearance. And what you want to do is go to the physical properties and expand all of these, and then you can just copy what I've got right here. Now if you're doing static stress simulations, the only thing you're mainly going to be interested in is the Young's modulus, this property right here, and that's a property that affects the stiffness of the material. It describes the stiffness of the material, yeah. Another handy thing to enter could be the density of the material. If you want to calculate the deflection to stiffness, the deflection to weight ratio. That's I'm not sure if that's a legit ratio, but that's what I use to determine what design is the best. But we'll talk about that in the next video. Alright, enough about that. Another thing actually. Epoxy granite, it can be some kinds of epoxy granite is a bit stronger than others, and that mainly depends on how well you mix it up and how well you fill it in to your cavity or profile or whatever. But I've read on forums that the maximum strength that you can get with epoxy granite is that it is if it has what happened? Is that it is if it has a Young's modulus of 50. So I'll make mine 50, and then I'll press apply and OK. So we're using we're a bit optimistical using the stronger kind. Okay, now it looks a bit weird. Our epoxy granite, it's just grayed out. That's just because I'm too lazy to give it an appearance as a material. So I'll just select Granite from the Fusion library and apply that. And if we make it at a scale of 25, then it looks a bit better than it did before. Okay, finally, now we are ready to enter the simulation workspace. And I'll just go ahead and give it some constraints. Important thing to note, again, is that we don't want to select our epoxy granite. We will not have our epoxy granite mounted to the legs of the gantry. If I go under the materials section, you could see all the properties for our materials that we are using. Okay, let's go ahead and apply our loads. 1400 newtons, minus 150 millimeters, and now we are ready to solve. Okay, we are in the results section once again, and I'm going to go ahead and look at the displacement. Okay, this is really interesting. We have a displacement of 0.0046. That's 50%. It's actually 54. Wait, if we round that up, it's more like 53% better than the first beam. But now don't get caught up by the fact that it's stronger, because we also have a lot more weight added to this beam. So obviously it would be stronger. But what would be interesting is to take a look at just how much heavier it is compared to the first beam. So one might think, yeah, well, if it's 50% stronger, then it would weigh the double. Okay, so to get the weight of the entire beam, we can just expand the bodies folder. And usually you can select all the bodies and go to properties, and you should be able to see the mass right here. Now I see that it gives us a bit of a weird number, and I had some issues with this, but my way around that is just to select fewer bodies, and then we get a correct number. So we can see 7 kilos for these two bodies. Then we'll look at the remaining, and that's almost 6 kilos. So 7 plus 6 kilos, that would be 13 kilos. So that's actually not that bad. Let's compare it to the weight of the first beam. And this one weigh 9 kilos. Okay, so from that we actually know that this beam is a lot stronger, and it has a lot less deflection relative to its weight compared to the first beam. So this would be a better option, but one thing to bear in mind is that it's also a bit more complicated to build, and the availability of the tubes that are as thick as this one is not as great as just buying some slabs. These slabs are really common and easy to come by. So in more aspects, this one is harder to get your hands on. But enough about that. Let's go ahead and create the last beam for this video. Okay, now the next beam is going to be really interesting, because it will be two separate bodies. Now I've already gone ahead and found the correct dimensions to make this have the same area as the first and second beam. So I'll just enter these values, and the bottom one 75 by 25. 25, and we'll make the distance between those 120. Yeah, that looks about right. Okay, I'll make a line between these two corners, so that I can make the center point of this line join the origin. That basically means that we have made it symmetrical, as we'd like. I'll go ahead and extrude these I'm making 600. Okay, and then we can make our rails. Now, if I've made this correctly, the distance from these should be the same, 47 something. And it's not. Okay, whatever. I'm just going to go ahead and make both rails in one setup this time instead. And I'll make the midpoint of this. The midpoint of this during that, and this for that. And we will make them 20 millimeters. There we go. Yeah, that looks right. And we can extrude both to the end of the beam. There we go. And we'll make them new bodies so that we can apply separate materials. Okay. So I will add aluminum and stainless steel, and we should be ready to enter the simulation workspace. Now remember, we have not saved our part yet, so it will ask us to save it if we press solve. I'll show you that in a second. We'll just create our setup first. Oh, remote force, 1400 newtons. Okay, there we go. Now you see, if I press solve, it will ask me to save it. Now I'll save it as beam number 4. Okay, now we have our results calculated, so we will take a look at the displacement. And what we will find is that we will have a displacement of 0.014. And you can see it's at the top, but you can also see that the proportions is pretty balanced. The bottom one is almost red too. So let's compare this to the first beam. Let's see how much it weighs. I'll go into the design section, and we can see that the whole thing weighs just about 9 kilos, and I forgot what this weighed. I'll just select these bodies, and this one weighed almost 9 kilos as well. So if we go into the simulations workspace for this one, we can see that it has a displacement of 0.01, and this one had a displacement of 0.13, I believe. Almost 4 actually, 0.014. So that basically means that this design is really not that strong. It's actually weaker than this design relative to its weight. So now we know that we should not design our CNC this way. Alright, that's actually all the beams we will be simulating in this video. Now off camera, I'm going to simulate a lot of different beams. I already have actually, as you can see here. And then in the next video, we will discuss the results and and then we'll pick some beams to create further variations of and investigate their design to find the optimal proportions. Alright guys, I'm looking forward to seeing you in the next video. Take care and bye bye.